Hey, good morning, everybody. So yeah, happy Tuesday, everyone, and I also hope you had a great 3-day weekend. If you got 3 days off, that's awesome. All right, so how is everyone? Excellent. All right, so we made it through PA1. And people did a fantastic job on this assignment. I was so impressed. So the commenting was excellent, right? Almost everybody had the required commenting in the front of their functions, which is fantastic. So I saw, function names, definitions, explanation of the function, list of inputs and outputs. That was great. Almost everybody had the comment block, and I think everyone had the comment block in the beginning of their main program, which means everybody had their name on their code, which is also excellent. Consistent indenting throughout, no issues that I saw with coding style aspects, so that's great. The make files were excellent. Almost everyone make file worked perfectly. And most people modularized the heck out of their code, which is excellent, because I didn't require you to break this into separate files. Most people did. And hopefully you're finding, a level of modularizing that works well for you, and hopefully that's making sense to split things up. So this was a really easy assignment to grade, because a lot of people, the code just worked great. Most of the deductions that I gave were actually silly things, right? Something different in the output style, using a different command, using A to insert instead of I, for example, or having a function with a different name from what it's supposed to, things like that. Things that have nothing to do with the underlying structure of a linked list, right? And so that's really good. And almost everybody processed their data as a linked list, meaning starting from the sentinel and working through the list to do all of the required manipulations, and that's good, because that's going to help with PA2. So yeah, no worries on my end for where people are as far as the assignment. If you didn't have code that compiled, or if you had code that did something fundamentally different from what it was supposed to, right? I gave you some feedback in the comments. Definitely look at your comments on Canvas. If you got 100, there's no comments. Okay, basically means everything was perfect. So look at your comments on Canvas. Let me know if you have questions about those. And PA1 will lead into PA2, and we'll talk about PA2 towards the end of the week. So really nice work on that first assignment. Service learning project. So I got through people's proposals, and I left you feedback if I had any issues with that. If you got the full 25 points, you're good to go. If I had any issues with your submission, I left you comments, and you did not get a grade. Or in a few cases, I might have given you a 0 and said, let me know when you resubmit, and I'll regrade this. This was due last week, but you got to have a good proposal, because you're going to be doing this for the next 2 quarters, right? So you can turn this in late, and I'm not going to take off late points if you turn it in promptly, right? But if you didn't get a grade, there's a problem with your submission, and it was still due last week, so you need to get it resubmitted. You need to get it corrected and resubmitted as soon as possible. All right, so make sure that happens. And mostly it was a question of needing more details, right? So again, if you just take that list of topics that I mentioned and you just write 1 or 2 sentences next to each one, that's not a proposal, right? So it's got to be a full document. And the other thing was detailed milestones. So the milestones have to be measurable, which means it has to be more than, you know, make some progress by week 5. There's got to be something that we can quantify. So SLPs look good. Keep going forward with those. And let me know if you have questions about it. All right. Any lingering questions on PA1? Or any of the other stuff we've been doing? All right, let me mention 3 things to keep in mind for PA2 and in general. First thing, right? Remember, when you're defining a set of functions to implement some behavior, for example, you were building basically a library of functions that can be called to manipulate a linked list. Okay, so that's a package, right? That's something that, you know, presumably somebody might download because they want to use a linked list in their code, right? You want your functions to do exactly what your specification says. In particular, you generally don't want to print anything from your functions except for the print function, obviously, right? In your search function, if you don't find a node, don't print a message saying node not found. Because, you know, somebody might be using that function to, I don't know, you know, search thousands of different entries, and you don't want each one to generate a message to stand it out saying, you know, node not found. Same thing with deleting and inserting. So think of these things as function calls, right? Imagine if every time that you called the square root function, it printed a message to your screen that said the square root is and showed you the square root. That would not be terribly useful, right? If you were writing a program to solve the quadratic equation and you were using that, you know, famous formula that has a square root in there, you wouldn't want a message coming out in the middle saying the square root is, right? So think about these things as units that somebody potentially different from yourself might call. So that's one thing. Second thing, make sure you comment your main program. It was interesting. I didn't explicitly say put comments in your main program, and most people did not put comments in their main program except the comment block at the top. There's a lot of code in main. There's a lot of parsing going on. There's a lot of conditional statements. Go ahead and comment that, right? And don't wait for me to tell you to comment something to comment it, right? Comment everything and really try to move towards commenting while you write the code. It will help you. Okay, and I guarantee when you get to your destination university, WSU or PSU or wherever you're going, people around you are going to be complaining when they get their grades, saying, "Oh, I lost 30 points because I didn't have comments," or "Oh, I got a 0 because I named my program wrong, or I used the wrong function name, or I took in an integer instead of a float," you know, or something. And you're not going to be that person, right? If you continue what I'm seeing so far, right, you're going to be successful at following assignment prompts and taking care of details and you know, putting things in Git and putting in comments and a consistent coding style and all that kind of stuff. It's going to help you down the road, right? So these are really good habits. School is like 60% following directions, yeah, definitely. And you're really training yourselves, right? So I'm just kind of trying to like guide you in directions that I think will help you down the road. But it's everyone here that's doing all the hard work, so that's really good stuff. Yeah, turning a float into an int probably isn't something you do, but yeah. Okay, cool. Let's see. All right, thanks. So let's talk about pointers. I don't know about you, but I draw free body diagrams for my own benefit every day. Cool. All right, so PA1, we built a linked list. It's a data structure. We created nodes. We had them point to other nodes and so on. And the nodes in question were elements in an array. But that was just, you know, a simpler way to find areas of memory that we could use. But there's a more general way to do this, right? Which is to basically ask the system to give us a block of memory. And so when we want to make a linked list without having a predefined, you know, pre-sized array of nodes, what we're going to do is we're going to make a call to the system using malloc, right? So you've bumped into malloc before probably. We're going to use malloc and say, hey, give me a block of memory that's big enough to store a struct node. And we'll get that back. And then we're just going to kind of use it the way we did in PA1. We're going to set up the fields of it. And we're going to build up a linked list of it. So let me show you what our structure is going to look like. So our node is still going to have a data field. And if we're making a linked list of integers, we're going to, you know, have an integer data field. But our next field is going to be a pointer to a struct node. So this is a little weird, right? We have a struct node that contains a pointer to a struct node. But it's really no different from what we were doing in our PA1 version, right? In PA1, this next field was basically a reference to another struct node, even though it was inside a struct node. A pointer is really just a memory address. So this next field is a memory address. And it says where in memory is the next node that builds this linked list. And so when we want to make a node of this type, we could do something like this. And Sentinel would be a struct node. So let's play with some code. Well, it's Typo Tuesday. Alright, so let's make a structure. Alright, so, yeah, good thing it's ignore warning Tuesday because it's also Typo Tuesday. So Sentinel is a struct node, right? And so we can say sentinel.data, we can say sentinel.next. So let's just build a small list by hand. So let's put together something like this. We'll do sentinel. And I'll make a node called first, and I'll make a node called last. And we're just going to play with this right now. We're going to cobble together by hand a linked list containing a Sentinel node and two data nodes. And we're just going to play around with it inside GDB and mess with some code and generally have fun. So let's make a... oh, I just did something I didn't want to do. Okay. Very good. So let's do first and last. So we've got 3 sentinel nodes. We're not doing any mallocs right now. So we want our sentinel node to point to the first node. Okay. So I want this next field to have the address of the node first. So how do I find the address of a variable in C? Use an ampersand. Good. So I'm just going to say address first. And I'm going to say first.next equals the address of second. And what do you think we're going to set second's next equal to? Hope it's actually last. Yeah, we're going to set it equal to my null, except in C it's going to be called null. I can honestly never remember if it's uppercase null or lowercase null, because I don't actually use it. So we'll find out when we compile. Well, let's just compile it. Hey, we got it right. Alright. So it's uppercase null. That is a built-in symbol for you. It's defined in standard.io.h. You always want to use that when you're looking for null. It's equal to a pointer to 0, but don't use 0. Don't use a pointer to 0. Don't use \0 in single quotes. Use null. Okay? Anything else is going to get you raised eyebrows and maybe warnings. So that's why we were using my null in PA1, right? So null is set up, and null will never be the address of anything in our Unix system. Right? So by putting this value null down here, we know this is not pointing to another node. And so that's a totally safe marker to use to say that's the end of the list. All right, so let's load some data values. So we'll just put a bogus value into our sentinel node. We'll put a 10 into our first node. We'll put a 20 into our last node. So we're building up a list that looks like this. And I'll just put a last statement down here so I can put a breakpoint there or stop there when I step through the debugger. So let's compile this, let's run it. Alright, so we've executed our code, we've presumably built up a small linked list. Let's print the value of sentinel. It's got the data value of 42, that was the bogus value we were putting in there. Yeah, so my null in PA1 was just to get you used to using null in PA2. And basically you're just going to change all your my nulls to nulls. So sentinel has a data value of 42. It has a next value of this. FFFFE3C0. So if we say examine this value, what do we see? We see hex A, that's the number 10. That's the data value of our first node. If we examine the next location in memory, we see 7FFFE3D0. Well, this pair, the number 10 followed by E3D0, that's the contents of our first node. If we print first, it'll show us first is a 10 and it's got a next value of E3D0. If we print the address of first, That's E3C0. That's the address that the sentinel is pointing to. And the first node is pointing to E3D0. And if we examine that location, we see a 14 hex. That's our number 20. And that's followed by a strange looking value. If we print out last, it tells us the next value is equal to null, right? And that its data value is 20. So the sentinel is stored at this location. And if we do a memory dump at that location, we can see our whole structure. Let's do a few more locations. Alright, so what have we got? At the address pointed to by sentinel, we find a data value, which is 2A. We find a 0, and then we find a 2-word address. 0000 7FFF FFFF E3C0. So there's a piece of filler here in between the data value and the next field. Now when we defined our structure, we said I want an integer called data and then I want a pointer to a struct node. But the way this is actually laid out in memory looks like this. Right, there's 4 bytes that store the data value. There's 4 bytes that are unused, and then there's 8 bytes that store the next value. That's not obvious from our C code that defined a struct node, but it's also not important to us. We don't really need to know this except when we're in GDB and we're trying to figure out what's going on because something went horribly wrong. But here's the sentinel node's data. Here's that unused word, and then here's the 16, the 8-byte 16 nibble address of the next node, which is at E3C0. Well, that's right here. There's the data value of the first node. There's the filler. There's the address of the next node, which is E3D0, which is sitting right here. There's the node value for last, which is 20. There's the filler. And there's the address of the next node, which is null. It's all zeros. So there's a linked list. And if you knew this node structure, and you knew that it was, organized like this, you could start with this location in memory and you could figure out what exactly the data structure was. If we're in GDB and we've compiled with debug symbols, we could also figure this out by doing the following. So we could print, right, we can look at the fields of Sentinel just by saying print Sentinel. We can print the address of Sentinel, right, which is the location where the first byte of this structure is stored, like this. We could also print the address of sentinel.data and see that it's also E3B0. That tells us that our data is stored right here in the first 4 bytes. I don't normally want to do sizeof on variables. I usually only want to do that on types, but I'm going to make an exception here. I'm going to look at sentinel.data and ask for its size, and it tells me it's 4 bytes long. Right? So that tells me that at the beginning of Sentinel, I have 4 bytes corresponding to data. And in this case, for Sentinel, they start at 3B0. Now, if we print the address of sentinel.next, that's where you see it's all the way down at E3B8. So let me make you a picture. So for the Sentinel node, E3B0 had the data. E3B8 is where the next field starts. That also tells us there's a 4-byte word that's being skipped in the middle. And one more time, I'll use sizeof in a way that I'm not going to encourage you, and look at the size of sentinel.next, and it tells us that's 8 bytes long. Right? It's 8 bytes because we're on a 64-bit machine here, and so addresses are 64 bits, 8 bytes. And then the way that the compiler and linker set up our memory storage, when I said I wanted a Sentinel node called first, it put that in the next location available. Right? It just stuck that in 3C0, so all the stuff ended up packed together. Didn't have to, right? Since each node has the address of the next node, right, I could have my Sentinel pointing to last and have that pointing to first, just by changing the values of these next fields. All right, the trick is you get to set this up yourself. You can structure it however you like. All right, so just as a sidebar, why is the compiler skipping 4 bytes between the data and the next field? Why not just pack everything in there? And we touch on this sometimes in Engineering 270. So this is something called word alignment. And even though we think of our memory as being organized as individual bytes, right? Each byte has its own address. And we can access the memory with any address we want. And we can get the byte that's stored at that location. But the hardware of most memory systems is not optimized for accessing individual bytes. It's usually optimized for accessing at least 64 bits at a time, starting from an address that's divisible by 8. And so if I wanted to access an 8-byte address that straddled one of these multiple of 8 boundaries, there's a good chance I'd end up doing 2 memory accesses. Whereas to pull out this 8-byte address, I can probably do with a single memory access. So if I didn't put in this extra filler here and I put the beginning of next right here and the end of next right here, my memory access would probably take twice as long every time that I tried to get a pointer to the next node. Right? That's a pretty serious performance degradation. So these are things that as a pure software-focused C programmer we might not care about. But when we start, dealing with actual physical hardware, these details become important. Now, when we're programming in C, a lot of these details are handled for us by the compiler. It knows about word alignments and things like that. If we were writing this in assembly language and we didn't know any better, we might, put an address at starting at a location that's congruent to 4 modulo 8, right? And suddenly our performance goes down the tubes. And it's a hardware aspect of the system that's causing that. So just some stuff to keep in mind, the interrelation between the hardware and software. All right. So questions so far. This is a totally static, hand-built linked list of 2 data nodes in the Sentinel. And we haven't done anything really with pointers except, you know, a couple of ampersands to get the address of a node in memory. But we're going to start building on this. All right, so let's dynamically allocate nodes. So this is where malloc's going to come in. So suppose you're writing a program where you're going to get numbers from the user and keep adding them to a linked list. And we're going to do like we did with PA1 when we wrote some code in class. We're just going to start putting things in the beginning of the list. So let's expand this. So we'll just read a line from the user, and we'll convert it to an integer using scanf. I'm not going to worry about error checking here. And let's make a new node. So we'll have a struct node, new node. Set the new node.data equal to the number, and let's do new node.next equals sentinel.next. So we'll have the new node point to whatever was the first node, whatever the sentinel was pointing to. And we'll have the sentinel point to the new node. Alright, so this is not going to work, but it should look reasonable at first glance. So we're going to get a number from the user called num. We're going to have a new node. We're going to set the data value to num. We're going to set the next field to whatever the sentinel was pointing to, and then we're going to have the sentinel point to the new node. And we'll print a message here so I can stop GDB. It's got to be the address of the new node. Alright, so we built up our list. We're going to get a node from the user, so I don't know, I'll put in the number 37. So we've got the number, we've got a new node data, so let's print new node. Right now the data is equal to 37. The next field is who knows what. Right, it's just some weird number because we haven't initialized it. So we're going to set new node next to be sentinel next. So now if I look at new node, the next field is something reasonable. If we examine that location, that's our 10. That was our original first node. And now we're going to set the sentinel to point to the new node. So right now, before we do this, the sentinel is pointing to that 10 node. Once we change the pointer, the sentinel is pointing to this thing. which is that node containing a 37, 25 in hex. So far our linked list looks great. Our sentinel points to 360. 360 has a 37, a filler, and then the address 340. And 340 is the node containing 10. And that points to 350, and 350 is the node containing a 20, and that points to null. Alright, so far what have we done? We've made a new node. We put a 37 in here. We change the sentinel to point there, and we change that to point to first. We started with just a 10 and a 20, the same code we had a moment ago. So where are you actually putting the nodes? They're somewhere in memory, right? So I created a struct node here, right? Gave a data value, adjusted pointers before and after it, so now it's squeezed into the middle of the list. But this is where things are going to break. So we'll call the print, which prints out, you know, added 37. We'll get another number from the user. So I don't know, I'll do the number 19. So num is equal to 19. Well, now I'm going to set new node data equal to 19. I'm going to set new node next equal to sentinel next. But let's look at what sentinel is. Sentinel has, let's look at new node. New node has a value of 19 hex, right? Or a value of 19 decimal. That's the number that we put in. It has a next address of E360. Well, E360 is the address of new node. So what I've done is I've changed my new node to be 19, and I changed new node to point to itself. Why am I pointing to itself? Because that's what sentinel was pointing to. All right. So what the heck is going on here? Get a data value. Set new node's data equal to that number. Set the next equal to whatever sentinel is pointing to. And then have sentinel point to our new node. Well, that works exactly one time. So here's the instant replay. There is our original list. Here's our new node that we put a 37 into, and we changed our linked list to look like this. So the sentinel was pointing to a 10 to a 20. We put a new node 37 in, so sentinel's pointing to that. Everything's fine so far. The next time we go through this loop, though, we get our new value, 19. We say new node data equals 19. Well, new node is this node right here. So this changes to a 19. And then we say point to whatever the sentinel is pointing to. Well, the sentinel is pointing to this node, so now new node is pointing to itself. And we've got a totally messed up linked list. The problem here is that when we had our new node with a value of 37, we want that to be preserved. The next time that we want to create a node, we need a different node. And just saying struct node, new node doesn't give us a new node. Right? It's the same node at the same location in memory. So this is where malloc's going to come in. So let me declare my struct node. And let me say new node is a pointer to a struct node. And down here, I'm going to say new node equals malloc. I'm going to tell it how many bytes I need for a new node. Well, I don't know how many bytes. If I counted up myself, I might think I need 12, but I actually need 16. So I'm not going to try to figure out how many bytes I need. I'm going to use the sizeof argument. I'm trying to allocate space for a struct node. So how many bytes do I need? Whatever the size of a struct node is. So I'm going to set new node equal to something that's that big. All right. Well, new node is not a struct node anymore. It's a pointer to a struct node. So if I want to access the data field, I have to say star new node. And if I want to access the next field, I have to say star new node. And when I want to set sentinel next equal to it, I don't need an ampersand because it is the address of a struct node. Right? These details are unimportant. I'm trying to get across the general idea of working with something that's an address in memory, right? And we'll visit these details of star and no ampersand and stuff in easier ways next time. So what's the overall scheme here? We started off with just a cobbled together list with a sentinel, 2 data nodes, 10 and 20. We have a variable which is said to be a pointer to a struct node. Inside our loop we call malloc to find the address where we can store this much stuff. We set new node equal to that, and at that address we take the data field, store our number. We take the next field and set that equal to whatever the sentinel was pointing to, and then we set the sentinel to point to our new node. All right, if you do malloc, you need to do standard lib. So let's put in the 37. Let's put in the 19. And let's look at our list now. So our sentinel points to this crazy looking address. If we look at that address, we find the number 19, 13 hex, followed by filler, followed by this interesting address. And at that location we find 25 hex, that's 37, that's our second node. Filler, that's the address of our third node. That's where we find our number 10, filler, followed by the address of our next node, which is the number 20, followed by filler, followed by null. So we've got a genuine list. Which looks like that. And we can keep doing this as long as we like. And the whole trick, the whole reason that this works is because every time we want to add a node to our list, it's sitting at a new location in memory. Right? When we want to create a new node, we call malloc, which will give us a new location in memory. So when we call malloc 16, it gives us a location that we can store something in memory. And every time that we call this, it gives us a different location. And if we ask for 160 bytes, it gives us a very different location. And the next time we ask for 160 bytes, it gives us something that's 160 bytes beyond that or more. Now if you ask for too much memory, right? Oh, that's way too much. Well, it actually allocated that. Crash my machine. If you ask for too much memory, you get back an error indicator. And the error indicator is that malloc returns null. So malloc normally returns the address of a block of memory where you can store that many bytes of information. How many bytes am I asking for here? That's 1.5 gig. Wow. But if you ask for too much memory, right, and it can't find a spot available to store that much information, you get back null. That means you're out of memory. So malloc is going to take the place of getNode from PA1. And just like with getNode, after we call getNode, we need to check the return value and see if it's null. If it is, we're out of memory. If it's not, the value we got back from malloc is the address where we can store a struct node. And we store a struct node there by basically taking a variable that's defined to be a pointer to a struct node and setting it equal to that address. Right, remember if new node is a pointer to a struct node, it should have a memory address in it where that node is stored. Well, here we're actually loading a value into that address and saying, hey, the address of this node is whatever address malloc gave us back. So malloc is exactly like getNode, yes. But it actually goes out to the pool of available memory in something called the heap, and it pulls memory from there. And it takes care of marking that memory is in use, so it sets something like a valid flag, so that any time that you call malloc after that, you don't accidentally get the same block of memory back. Right? It marks it as being in use, which is what we did by setting the valid flag ourselves. I'm wondering if I'm killing my memory. I'm doing okay. All right, so that's a high level view of linked lists. We're gonna spend this whole week and a good chunk of next week really drilling down into the details of this and working through it pretty carefully. But that's basically the dynamic memory version of what we were doing with an array last week and the week before. And the real magic of it is this malloc statement. And then there's some syntax that we're going to deal with, and we'll make this really pretty tomorrow, so we don't have to have asterisks sitting inside parentheses. But this is, the struct node, right, which we get by taking a star in front of the thing pointing to a struct node. So this is just a struct node. And, we can say struct node.data, struct node.data. Well, that's all we're saying down here, struct node.data, struct node.next. And then when we want to have something refer to that, when we want to set the next field, in this case of the sentinel, it's just the name of that node, right? Why? Because this isn't a struct node, this is the address of a struct node. How do we know that? Because we declared it to be a pointer to a struct node. All right, so meditate on that, right? Let it percolate, and we'll come back to this tomorrow, and we'll go through it again, more on paper next time, and then start digging into some of the syntax. All right, so I will see you tomorrow. Have a good afternoon.